Hello everyone, and welcome. Today, we are diving into a fundamental concept in gas chromatography, retention time. We'll break down how to calculate it and what those calculations really mean for your results. Understanding these numbers is key to mastering your GC analysis, so let's get started. First, let's define the basic retention time, which we call T_R. This is simply the total time a compound takes to travel through the entire GC system. The clock starts at the moment of injection and stops when the peak for that compound reaches its maximum height on the detector. However, not all of this time is spent interacting with the column's stationary phase. A portion of it is just the time it takes to travel through the column's empty space. We call this the dead time, or T_M. You can measure this by injecting something that doesn't interact with the column at all, like methane. Think of T_M as the baseline travel time for any compound. To get a more meaningful value, we calculate the adjusted retention time, or T_R. This tells us the actual amount of time the analyte was retained by the stationary phase. The calculation is very straightforward. You subtract the dead time from the total retention time. So, the formula is T_R equals T_M. This value is critical because it isolates the chemical interaction from the simple travel time. From there, we can calculate an even more important parameter called the retention factor, or capacity factor, which we label as K. This is a unitless measure that describes how strongly an analyte is retained. The formula is K equals the adjusted retention time divided by the dead time, or K equals T_R/T_M. For example, a K value of 3 means the compound spent 3 times longer in the stationary phase than it did in the mobile gas phase. Ideally, you want K values between 2 and 10 for good resolution. Finally, we can assess the separation between two adjacent peaks using the selectivity factor, or alpha symbol. This tells you how well the column can distinguish between two specific compounds. To calculate it, you divide the adjusted retention time of the later eluting peak by the adjusted retention time of the earlier eluting peak. So, alpha equals T_R 2/T_R 1. For any separation to occur, alpha must be greater than 1. A larger alpha value signifies a better, more distinct separation between those two components. So, by using these simple calculations, adjusted retention time, capacity factor, and selectivity, you can gain a much deeper understanding of your chromatogram. It moves you from just looking at peaks to truly interpreting the separation. I hope this breakdown was helpful for you. Thank you so much for watching. If you found this video useful, please consider liking, subscribing, or leaving a comment below. Your support helps us create more content like this. See you in the next video.